In this video, we're going to discuss the proof of the division algorithm. The standard statement of the division algorithm that you'll see in most textbooks is as follows. Let m and m be integers with n greater than 0. Then there are unique integers q and r so that m is equal to n times q plus r, and 0 is less than or equal to r, which is less than n. So there are a couple differences between this standard statement of the division algorithm and the statement that we are going to give and prove in this course. Firstly, at this point in Math 323, we're restricted to the natural numbers, and we don't have 0. 0 is not a natural number. So we first need to restate the division algorithm to avoid referring to a number that's not in our number system. To do that, we'll just break it up into cases and state the division algorithm as follows. If n and m are natural numbers, not integers here, but natural numbers, and n is less than or equal to m, then first there's either a quotient q in n, a natural number q, so that m is equal to n times q, or there are natural numbers q and r, so that m is equal to n times q plus r, where the remainder r is strictly less than the divisor n. Okay, so you'll notice that we just avoided the reference to 0 there by breaking it up into cases. The first case where n evenly divides m, and the second case where there's a remainder. We still insist that the remainder be strictly less than the divisor, but you'll notice one other difference between this statement of the division algorithm and the previous statement. The standard statement of the division algorithm says not that just that q and r, the quotient remainder, exist, but it'll say that there are unique integers q and r with these properties. Okay, a unique quotient and unique remainder with the property that the remainder is strictly less than the divisor. Our version didn't say anything about uniqueness, and it's not because uniqueness isn't important. Uniqueness of the integers q and r is very important, and it still holds here over the natural numbers. We would still get unique quotient remainder. It's important if you're studying algebra or number theory. If you're seeing the division algorithm in a context of a course like that, you certainly would include uniqueness in the statement and proof of this theorem. But here in Math 323, we're going to omit it since that particular property is not needed for the future results in this course. Our proof of the division algorithm is going to rely on a handful of basic properties of the natural numbers. The properties we'll use include the following. Trichotomy. Recall that trichotomy of the ordering on the natural numbers says that for any two natural numbers n and m, exactly one of the following relations holds. N is strictly less than m, n is equal to m, or m is strictly less than n. We'll use the fact that multiplication by natural numbers preserves order, or respects order is another way of stating it. We'll use our subtraction property over the natural numbers, that if n is strictly less than m, then there's a difference between them. There's a natural number k, so that m is equal to n plus k. We'll use one of our cancellation properties for addition. So if you have natural numbers n, m, and k, and the sum n plus k is less than the sum m plus k, then n is less than m. And we'll use the well-ordering principle that states that every non-empty set of natural numbers has a minimum element. I think there are a couple other properties that we'll use. We'll certainly use the distributive property. I just wanted to call attention to these so that you remember them for the proof. Okay, so again, let's just state the division algorithm one more time before we get on to proving it. We have that if n and m are natural numbers with n less than or equal to m, then either there is a quotient q in the natural numbers, so that m is equal to n times q, or there's a quotient or remainder, a q and r in n, so that m is equal to n times q plus r, where the remainder r is strictly less than the divisor n. Okay, so this is an if-then statement. So it's if these things hold, then the following things hold. And so one way of proving an if-then statement is directly by assuming the hypothesis. So the hypothesis here would be that n and m are natural numbers and n less than or equal to m. So let's begin our proof by making that assumption. So we'll assume n and m are natural numbers, and we'll assume that n is less than or equal to m. Of course, we could have assumed that m was less than or equal to n, but we have to choose one or the other, and the proof is the same either way, so we just have to pick one and go with it. Okay, so we've made that assumption, and now let's define a set of natural numbers S as follows. S is the set of all natural numbers so that the product n times k is greater than or equal to m. S is a set of all k so that n times k is greater than or equal to m. This is a set we'd like to apply the well-ordering principle to. But to apply well-ordering to a set of natural numbers, you have to know that that set of natural numbers is not empty. And at this point in the proof, we don't really have many candidates for a natural number that could possibly be in the set S. Okay, you might think about, well, could 1 be in the set S? Could 5 be in the set S? You'll quickly realize you can't determine it from the information that you're given. So let's look at the only natural numbers we have available to us, n and m. And if you thought about it for a minute, you probably would come to the conclusion that, of course, m has to be a member of the set S. Why is that? Well, n is a natural number, so we know it's greater than or equal to 1. We also know that multiplication by natural numbers respects order. M is a natural number, so if we take m and multiply it times the inequality n greater than or equal to 1, we get that m times n is greater than or equal to m times 1, which of course is m. Okay, so that says that m times n is greater than or equal to m, and the fact that m's product with n is greater than or equal to n makes it eligible for membership in S. Okay, so that proves our claim that m is a member of the set S. Okay, because n times m, of course, has to be greater than or equal to m. So that's great. Now we have a set of natural numbers, and that set of natural numbers, by our claim here that we just proved, has at least one element. It's not empty. That allows us to use the well-ordering principle. The well-ordering principle says that a non-empty set of natural numbers has a minimum element. Okay, so S has a minimum. Let's give it a name, and we're free to choose any name we like except for n and m, which we've already used in this proof. So let's call it P. Now, as the minimum of S, P has two properties. Firstly, we know it's a member of the set S, and secondly, we know that if X is a member of S, then P is less than or equal to X. Okay, P is, after all, the minimum of S. We're going to, at the beginning, as we continue the proof, we're going to start by focusing on that first property, that P is a member of S. But for future use, let's just recall that we can restate this fact, this second statement, as follows. Instead of saying that members of S are above P, we can say that anything less than P is not a member of S. Okay, so we can phrase the second fact about the minimum P as follows. If X is smaller than the minimum P, then it can't be a member of S. Okay, if X is less than P, then X is not an element of the set S. Okay, so back to the first property. P is a member of the set S. What does that mean? Well, recall we defined the set S to be all natural numbers whose product with n is greater than or equal to m. Okay, since P is in that set, it follows that P times n is greater than or equal to m. Now, since n times P is greater than or equal to m, that means one of two things happens. Either n times P is greater than m, or n times P is equal to m. Okay, that's a pretty obvious observation, but it does give us two cases that we can consider to finish the proof. So let's take the easiest case first. Let's assume that n times P is equal to m. Alright, well, then we'll just take Q to be P. Then m equals n times P, which is, of course, n times Q. And since Q is a natural number who's such that n times Q equals m, we've exactly found a Q that the first possibility in the theorem promises us will exist. Okay, if you go back and look at the statement of the division algorithm, it said the first case was there exists a Q so that m is equal to n times Q. All right, in the case we have here, case 1, we'll just take that Q to be P. All right, and then that's it. We've proved that the first conclusion in our theorem can occur. So under this case, under the assumption of case 1, we've shown that there's a quotient in the natural numbers, a quotient q in n, so that m is equal to n times q. And that finishes case 1. So now let's deal with the slightly more complicated case 2. Okay, so case 2 is where n times p is greater than m. All right. Now, recall that p was chosen as the minimum of s. All right. We assumed at the beginning of our proof, way back at the beginning, that n was less than or equal to m. Okay, so n times 1 is less than or equal to m, and m is strictly smaller than n times p. Okay, so we have n times 1 is strictly less than n times p, which means that p couldn't possibly be 1. And since p is a natural number that's not equal to 1, it has to be larger than 1. So 1 is less than p. Now we can apply our subtraction rule again. So since 1 is less than p, we can find the difference between them is a natural number. So we can say that there's a q in the natural numbers so that p is equal to q plus 1. Okay, now here's where we're going to use the second property of p being the minimum of the set S. Since p is equal to q plus 1, q itself is smaller than p. And since p is the minimum of S and q is smaller than the minimum of S, q can't be a member of S. Okay, so that was our restatement of the second property of being a minimum. Okay, so q is not among the natural numbers whose product with n is greater than or equal to m. Okay, so n times q greater than or equal to m cannot be true. Okay, so n times q is not greater than m, n times q is not equal to m. So by trichotomy, we have to have n times q is strictly less than m. All right, and again, we'll apply our subtraction rule. So n times q is smaller than m. That means there's some difference between m and n times q. Let's call it r. Okay, so by our subtraction rule, there's a natural number r, so that m is equal to n times q plus r. Okay, now this is exactly the form of the second alternative in the theorem in our statement of the division algorithm. Okay, there's just one more thing to prove here before we can say we're done. We know that m is equal to n times q plus r in this case. Okay, but to finish the proof, we have to show that that remainder r is smaller than our divisor n. Okay, so let's do that. Now we still have our case 2 assumption. This is still case 2. So we still have our case 2 assumption that n times p is larger than m. Okay, so let's just chase through a quick calculation with this. Okay, so m is smaller than n times p. Okay, p is equal to q plus 1. So we can multiply n through q plus 1, and we see that m is strictly smaller than n times q plus n. Okay. Now back in the previous slide, we had just seen that m is equal to n times q plus r. Okay. So m is equal to n times q plus r, and that's strictly smaller than n times q plus n. Okay. And here's where we're going to use our cancellation property, one of our cancellation properties of addition. So on the left-hand side of that inequality, and on the right-hand side of that inequality, we have n times q. All right, so by our cancellation property, we can cancel the n times q from both sides of the inequality, and we're left with r is less than n. All right, so under the assumption of case 2, we've just proved that there are natural numbers q and r, so that m is equal to n times q plus r, and r, the remainder, is strictly smaller than the divisor n. Okay, so if we start with our assumption that given natural numbers n and m with n less than or equal to m, we've shown that one of two things must happen. Either there's a q in the natural numbers so that m is equal to n times q, or there are natural numbers q and r so that m is equal to n times q plus r, where the remainder is strictly less than n, the divisor. And that completes the proof of the division algorithm. Thanks for listening.